Hello everyone. I'm Mohamed Gaber. I'm a graduate research associate at the American University in Cairo, working as part of the Open Hardware Lab, and I am the lead maintainer of OpenLane over at eFabless Corporation. DFFRAM is also by Dr. Mohamed Shalan, the principal investigator of the Open Hardware Lab and the host of this event. I'm going to give you a little background and motivation for what DFFRAM is and why we felt the need to make it. Now, as you all know, chips need RAM. It's where you store the most basic information about, it's where you store a program, it's where you store your data, and thus every system on a chip typically has some random access memory on board. Now, it is larger than the commodity RAM you can buy, but it does match the speed of the CPUs, which makes it invaluable for this kind of thing. Now, PDKs, which is the physical data for a certain manufacturing process, usually includes a set of standard cells. Now, the problem is these standard cells usually include SRAM cells, but the very first open source PDK, Sky 130, did not include SRAM cells. It only included typical storage units. And so we needed some form of memory for the initial iterations of Caravel and the initial designs for Sky 130. Now, synthesizers will actually they'll attempt to translate big registers files into memory when they find it, but in case they don't, they just try their best to generate memory using standard cells. So they will synthesize the proper flip-flops or latches, connect the multiplexers and decoders and try to come up with memory. And they do a fairly good job of it given the circumstances, but it is still ultimately inefficient. So, and you couple that with the fact that placers can't handle this memory very well. So if we compare here RAM that has been synthesized and placed versus RAM that has been designed from scratch in silicon, you can actually see that it's pretty much like 15%. It has 15% of the density of the custom crafted RAM, which is obviously a lot of wasted space. The more space you can save on RAM, the more you can include for other components. So we have two problems here. A, synthesized memory is inherently inefficient, but B, placers waste a lot of space trying to place them too. You can see here I have a small image. You see a lot of empty space between the cells. So that's not tenable. And we do need a better way to do this. So we started working on the DFFRAM project. Now, initially, we just made a handcrafted netlist. So we didn't have a custom placer yet, but we just had a netlist written, in Verilog, just the cells themselves, no register file, no regs, no wires, nothing, just the cells, right? You can use either latches or flip-flops, and it is based on a building block pattern, which means you can, here you can see, for example, the circuit diagram representing a single byte. Well, you can connect a couple of these bytes, and then you've got a word, a 32-bit word. You can have multiple words to form a slice. You can use a couple of these slices to form even larger pieces of RAM, etc. So you take the synthesizer out of the equation, you know what the counts of your cells are, and you can control these cell counts. So, you don't have to keep adding cells that may be wasting some logic. You know exactly what cells are being used, so there are no foreign cells in the equation, and you know the exact timing for these cells. So there's no buffer insertion coming in and perhaps ruining some of the logic. You know everything from start to finish. But still, that doesn't solve the placement issue, though. I mean, placement algorithms are by nature heuristic and inefficient. They try their best. I mean, other than this Google AI placement algorithm, which is actually very interesting, and I recommend checking it out. But while those do more fine for most designs, for RAM we already know the structure. I mean, it's just a bit and a buffer, a bit and a buffer, a bit and a buffer. Now, placers will just place them randomly to to find a local minimum for the total wire length, but we know where we can place them and we can do a better job. So we set out to do three things. Update the netlist so even some cells usually considered filler, such as diodes, are included. Right? Write a custom placer that knows the structure of the netlist and uses it to achieve very high placement density, and maybe write a custom router if we need it, right? We might need a custom router, we might not. Spoilers, we did not. I'll get to why in a moment. But yeah, this is the beating heart of the DFFRAM project, which is the custom placer. It's a Python 3.6 based tool that uses the OpenDB API, and it is tied to the specific handcrafted DFFRAM netlist, but it's pretty modular, so it can pretty easily adapt to changes or, expand, shrink, etc. Now, it works in two distinct steps, sieving and placing. We'll get to those in a moment. So now, even though it's a handcrafted netlist, we still do need to elaborate it. Why? Well, we've got parameters. Verilog does support parameters, and they do not actually introduce them in logic. And the others are Verilog generate statements. So we need to, for example, the same model needs to support both 8-bit words and 7-bit words, or 8-bit bytes or 7-bit bytes, and 64-bit words and 32-bit bit words. So these all need to be part of parameters and generate statements. And furthermore, once the netlist is floor planned, the def files are flat. Def files have no they have no trace of the hierarchy that once existed. So the question remains as to how do we associate the existing def cells with internal data structures? Well, we take a little inspiration from nature, I guess. So we kind of run all of the instances through a filter and reconstruct the hierarchy that we once had in the Verilog. So the def actually has a small trace of the hierarchy in the form of the names. So we have regular expressions for words, for bytes, for decoders, and whatnot. And by the time all of the cells have passed through all of the filters, we've actually reconstructed the hierarchy for the RAM here. So this is very, very advantageous, as you'll see later. But essentially, we've reconstructed the hierarchy. So now we have all of the data in data structures that we can use. A very simple data structure such as bit, byte, word, slice, and block. Right? And then you can type bit.buffers or bit.storage elements, and then you just get the cells that you require. So the placement uses the row object, a custom abstraction over OpenRoad ODB rows, which exposes APIs that is then used by the data structures we created to place their cells along a certain row. It automatically handles insertion of tap cells. One must be inserted every 15 microns or so, and I know we said we'd put diodes in the actual netlist, but tap cells would be an actual pain in the butt. So we just made the row object handle them automatically. It does expose an API to quote unquote fill a block of rows with filler and decap cells. So this little animation I showed you here earlier, that's actually how the row object works. You can insert cells into it and it'll automatically handle a tap cell when it's time. And the way you use it is incredibly simple. So for example, here I have some data input buffers. To place them, I just for diebuff in self-lib diebuffs, row.place diebuff. It cannot be simple. It handles everything. It cannot be simpler. Handles everything behind the scenes. Everything just works. So you can see here this is an example of a place byte. So we've got do some decode logic, and flip-flop and a buffer, and a flip-flop and a buffer, and a flip-flop and a buffer. Now it's mirrored, so actually this flip-flop corresponds to this element here, and this buffer corresponds to this element here, right? So we do place 8 of them in a row, and then here's the decoding logic on the side. But the advantage of the modular hierarchical design that we have is that, well, we can scale up. So this is 4 bytes put side by side on one row, which creates one 32-bit word. And heck, you can put 8 of those to make a slice. You can see the route, and you can see here the routing that's going on, but make no mistake, if you take a look at one corner here, that's the very first byte that I showed you. And you can take 4 of these quote unquote slices to get a kilobit of RAM. And you can even keep going. This is 8 kilobits of RAM, which actually is probably this structure 8 times. So you can keep going. Of course, it's going to take a little bit more routing time, but you can theoretically go infinitely. Ultimately, we didn't end up needing a custom router because the custom placer, being hierarchy aware, enables OpenRoad Triton Route to construct short routes very quickly. So we actually, because we know the placement exactly, we can put components that need to be connected very close to each other so the router doesn't have any trouble. Plus, honestly, it's for the best. A complex router would have, a custom router would have been very complex because shifts in position because of iteration and tap cells and fill cells would have to be accounted for. So really, after placement, we just pass the rest of the design through OpenLane. So we, like Caravel has an interactive script that does everything, we constructed a similar one for DFFRAM that takes everything from PDN generation to GDS2 stream out and just does it through OpenLane. So DFFRAM handles placement and OpenLane handles the rest. And the results are actually significantly better. So it's obviously can be as good as, you know, custom crafted RAM cells such as OpenRAM, but these take a lot less time to port to a new PDK or develop. So you can see here we've had an easily a 4 times improvement almost over just pure synthesized memory. Now, granted, it's still not as much as OpenRAM, but it is still pretty respectable given that this is just standard cells being strung together. So yeah, conclusion, future work, we have a huge potential for these open source hierarchical placers for regular structures because it greatly increases the placement density of designs compared to OpenRoad's replace and I believe fastplace was the other one called. So this can be used for many other designs, including ALUs, really register files, which the DFFRAM also supports as well, by the way. Any structure that you know is regular, adders, whatever you can think of. And it's as much quicker to port to new PDKs versus designing custom SRAM cells. You can just, you know, you have these cells here, they're Skylon 30 cells, but there's really nothing stopping you from replacing them with OGF 180 cells or, you know, Sky 90 cells. I guess that's announced now, but it's not coming out for a while. So you can just replace the cells with equivalents in another PDK, and there's nothing stopping DFFRAM from theoretically working. So yeah, we're currently working on making the netlist PDK generic so we can port a GF180 MCU, and we are working on, and we are also working on designing ALUs, designing the ALU to work similarly. So thank you. This is a GitHub link to the DFFRAM repository. Please do check it out. And yeah, I'm ready for questions. So by the way, I have one last thing I'd like to mention. So there is a Google Collaboratory for DFFRAM, like right here. So what you can do, you can run standard cell library-based memory using DFF and latch cells. You know, it's just a matter of pressing the play button on a couple cells. If you have any experience with machine learning, you already know how to use these things, which is good because I barely do. But essentially, if you run every step here, you'll have placed and visualized your first RAM32 module. So it is pretty useful. It's been designed with help from Proppy from Google, who we thank dearly. But yeah, it just installs Python, installs all of your dependencies, and installs OpenLane, and lets you just place your first either RAM or register file just while you're just from this page. You don't have to download anything. So do please give that a try.